Hello and welcome everybody for this iteration of SPE Data Science and Engineering Analytics Technical Section webinar series. We are very glad to have you all on this call. It's a recorded webinar. Um, as just a quick logistics, during the webinar, if you have any questions, you can use the Q&A section in Zoom and start putting your questions. And at the end of the webinar, we'll try to get to as many questions as possible. And before I introduce my today's speaker and also the topic for today's webinar, I wanted to put a link in the chat for everybody to promote the event that SP DSEATS is hosting in the end of September in Houston area. It's AI for Energy Americas. It's an event that uh, we are planning for a long time, and it's going to be a little bit different from conventional events. So I hope to see some of you who are in Houston or your colleagues who are interested. Please spread the words, and we'd love to have you in that event. With that, I'll introduce today's topic. Today, we are going to talk about unlocking early water breakthrough detection in gas wells, integrating wellbore physics and data-driven methods to predict water-gas ratio. And our esteemed speaker for today is Utkarsh Sinha, who is a senior research engineer at Zekta Digital Labs. Utkarsh, thank you so much for your time and welcome to the webinar.
Thank you, Pushpesh, for having me here, and hello to everybody who's attending this. Thank you for attending this. Hopefully, we'll have some useful knowledge after this session. So, in this session, before we even introduce the session, as Pushpesh introduced, I'm Utkarsh Sinha. I work as a senior research engineer at Sector Digital Labs, where my primary job is to develop algorithms that combine machine learning data-driven workflows with the physics. So basically physics-informed modeling. And I did my master's in petroleum engineering from University of Houston back in 2018, and my undergraduate from VIT University in chemical engineering. So that's a little bit of bio. And let's move to what we are going to talk in this presentation today. So we're going to talk about how we can estimate water gas ratios by integrating the wellbore physics and the data-driven methods. And what that helps us to do is that in this particular case, we have offshore wells, 40 offshore wells from 8 different offshore fields. And we'll see how, if you don't have multi-phase meters, if you don't have a way of measuring reliably or water gas ratios, and you have the fear of aquifer influx, water breakthrough, and all those things, how you can mitigate those risks by predicting the water gas ratios effectively. So without much ado, let's move to the beginning of the presentation. So water breakthrough often caused by the aquifer enrichment, leading to reduced recovery, operational shutdowns, and other sort of interventions that you necessarily don't want. The issue with water gas ratios or water rates measurement is that the wet gas venturi flow meters don't measure liquid rates, and both condensate gas ratios as well as water gas ratios in the field change due to pressure during the depletion. And when you have aquifer influx, you have a clear case of water enrichment. Back allocation based fixed WGR may not be the best idea when you're actually predicting your water rates, even though your water rates will update every time you have a gas rate updates because of your back allocated WGR. But like I said, WGR is not a constant thing unless you don't have any aquifer influx and you're necessarily producing your cornet water saturations. But the moment your water saturations change because of an underlying layer of water, you will start seeing a rise in the water gas ratios, and therefore back allocation should be updated from time to time, and you need some way to update that. Now, occasional salinity and tracer measurements can be done, but those data are sparse. Salinity test can only tell you the salinity trends, but you cannot determine the water gas ratios from that. And max, you can tell that there is an enrichment of a source because your water salinity has changed from a time to a different time. And tracer measurement, again, is dependent on your interpretability and your accuracy of your tracer model. And there could be a lot of complexity in that and could produce non-unique results. So basically, our purpose is to timely detect water breakthroughs from the aquifer to enable proactive intervention and do things before time, which if not done, can delay the recovery significantly and increase your operational cost. And timely detection and effective monitoring is crucial for your well performance and hydrocarbon recovery. But like I stated, to be able to do so, there are a lot of gaps in the measurement of water gas ratios, which I discussed briefly, but we'll discuss more in the next slide. So some of the common methods that we use to measure the water gas ratios are, test separators. But one of the issues with test separators is that um, in offshore, you wouldn't, first of all, see a lot of test separator due to high cost, weight, space constraint. And also understand that you can, in offshore, if you have one test separator for each well, it's ideal, but you cannot have it because you have too many wells. And if you have one separator connected to multiple wells, the problem is you again rely on back allocation on per well basis of water gas ratios, which is not ideal, right? And then obviously undersized unit of separators can lead to phase carryover and therefore inaccurate water gas ratios or measurement. Single well tracer test, again, like I said, it's nice, but it's qualitative in nature. It's not quantitative. It's dependent on your model assumptions in your tracer models. And then in a complex heterogeneous reservoir, it can also produce non-unique results. So, it will be hard to actually quantify what is your water gas ratios just based on the concentration that you receive at the outlet of that you receive based on what you get towards the end of your tracer test. MPFMs are ideal because they use a combination of sensors to measure real-time flow rates, but they have their own sensitivity issues. First of all, they're sensitive to PVT variation, so they have to be recalibrated from time to time. Logistically and financially sensitive, and they are susceptible to complex flow dynamics, especially if you have solid asphaltenes, emulsions, and those kind of things. And they demand expert operation because of the calibration, that errors that have to be calibrated, retuned time to time. There could be operation failures. So these are some of the gaps in the measurement of water gas ratios especially in a gas well. And because of this, we have something known as virtual flow metering, which are benchmark models which have been used from time to time. So two kind of virtual flow metering models which have been used extensively. One first is first principle virtual flow metering, which essentially uses which are grounded in physics, essentially use mass and energy conservation and use reservoir inflow performance curve, multiphase wellbore hydraulics, which is essentially your multiphase flow equation. Could be mechanistic, could be one of those correlations like which are semi-empirical, like Briggs and Brills and Beggs, Mukherjee and Brills, Hagedorn, Brown, Grays, etc. And could use choke models as well. So what does it do? Basically, it can predict your three-phase rates using some of the common inputs available, like downhole pressure, which is essentially a bottom hole pressure, temperature, wellhead pressure, surface temperature, choke opening pulse, and downstream temperature, downstream to choke. What are the limitations of these methods? First thing is that it requires known phase ratios like GOR or CGR and water gas ratios to estimate individual flow rates accurately. Now, this is the whole challenge here, right? We do not know water gas ratios and water gas ratios, especially in this case, because of presence of aquifer beforehand. And if we assume that constant, then we assume that there is no aquifer influx. But we do have aquifer influx, at least in these cases, and it's a common thing in offshore wells, right? In gas wells. So second method is data-driven virtual flow metering, which applies machine learning models trained on historical rates. It uses somewhat similar inputs as your first principle virtual flow metering, but it uses a data-driven model to relate the inputs to the outputs, with outputs essentially being your rates and inputs being similar inputs of what you have on virtual flow metering. It again requires three-phase flow data for training or some assumption on it, because not just training, but testing as well, right? And it is also sensitive to noisy data. Suppose you develop an ensemble method which can produce three-phase rates independently and may not consider let's say, the PVT data at all. Over there, you will lack a physical basis. and you will have difficulties in linking it to reservoir models or well models or anything downstream of your virtual flow metering models. So these are the issues. I mean, especially with data-driven method, if you produce three-phase rates as a part of your model without putting any PVT constraint to it, it can produce anything, and you may not see realistic trends in the GOR sometimes. So this brings us to the objective of this work and builds a nice case of why we are trying to do all this, right? We are trying to build a water gas ratio prediction method. And here, in most of the cases, like I said, you don't have any MPFMs rates to calibrate, any historical rates to calibrate or train the model. So the training is based on physics definition of water gas ratios, which is that if you use water gas ratios in a multi-phase model of your choice, like I said, anything, be it mechanistic like Ansari, or be it a very empirical and basic model like Hagedorn-Brown, you can plug this water gas ratio that you predict from your model and see how your BHPs compare to the bottom hole gauge BHPs that you have in bottom hole sensors, bottom hole pressure sensors gauges that you have in the field. And what it does is that it can tell you whether your water gas ratio is correct or not. But on the other hand, you can also tune your water gas ratios in real time from the real time pressure measurement. What it does is it gives you a real time water gas ratio, which can also tell you real time water gas breakthrough water breakthrough detection, which is helpful for your timely intervention and mitigation. And based on that, you can also optimize your production and calculate derivative properties, and plan your downtimes, maximize hydrocarbon recoveries. So let's look at the model. What does the model look like? I mean, this is the key part. What we are taking into the model is your delta P1 and delta P2, representing your inflow and outflow pressures. Essentially, in this case, it would be bottom hole pressure and the wellhead pressures. Bottom hole pressures are measured from your gauge measurement, and your wellhead pressures are known from your surface measurement. It takes the gas rate, which is coming from the wet gas Venturi meter, and the PVT, which gives you informations like CGR and viscosities and densities. Now, what we do is we predict the water gas ratios based on this. So some of the things are like, one thing is that you predict your water gas ratios using this. See if that what kind of BHP match you get with that water gas ratio. If the match is poor, you retune your coefficient. So we take the part of bottom hole pressure matching is the physics part of it, where you use a physics-based equation, a multi-phase flow equation, to predict your bottom hole pressure based on your water gas ratios and other information indicated here. And how do we even predict WGR that goes into the bottom hole pressure? That is through a data-driven model. So we have shown here how we predict our water gas ratio. By the way, this picture is motivated from our Berkeley-Leverett two-phase displacement of water and oil, or water and gas, basically immiscible displacement two-phase. And over there, you obviously have fractional flow of water here and water saturation here. So we've taken something derivative of that, and therefore this shape of the Berkeley-Leverett is similar to a 4-parameter, 5-parameter logistic regression equation. You can also think of it like a sigmoid shape. So these are the 5 parameters that control the shape, which is your initial asymptote, higher asymptote, your slope, and your point of symmetry, which essentially controls your water breakthrough. And what you can do is you can use these coefficients to tune your water gas ratio in such a way that you can match your gauge pressures perfectly if you plug in this water gas ratio into a multi-phase equation, considering the right flow regimes and everything else, considering the right physics. If you're able to do so, then you will get a great history match into your BHPs by tuning these coefficients, and that's going to be ultimately your water gas ratios. But what if there is a noisy BHP gauge data? How do I know if these water gas ratios are real or not? So luckily in these cases, we had some sparse tracer tests done, And we were able to map ourselves to tracer tests. But again, like I said, tracer tests are quantitative in nature. They could have other operational implications, so they're not always going to be always going to be accurate. So these models also help you in understanding that, okay, your gauge pressure matches well, so you have some trust on your model. On top of that, if you're able to match the tracer trends, you get more confidence on your model, and it helps you eliminate tracer data which is not so reliable because of operational condition, which we had benchmarked in this test, and we saw that. So let's look at some of the deeper understanding of this model. So it's a very simple model. Like I said, you collect your gas rate, you collect your wellhead pressure, collect your temperature wellhead, and you collect your gauge measured pressures. Then you also collect your measured WGR from sporadic tracer test or well test if available. And you collect your PVT information like CGR, viscosity, density. Then based on your WGR, you calculate your BHP. You solve a optimization function where you calculated BHP and gauge BHP error is calculated, and you have a penalty function. This thing is L1 regularization, and it is taking a penalty function of the water gas ratio that you calculate on the days of terrestrial measurement and actual terrestrial measurement. Now, please understand, this is very useful thing, because this regularization makes sure that your optimization is done with the constraint that you don't deviate. Your departure from your tracer measurement is the least, and that ensures that if you can get a pressure match within a certain range of match of your tracer measurement, you would do so, and that's what you want essentially, right? You see the convergence of this. If the optimization converges, you reconcile the results that you get in terms of your water rate with your measurement that you make at the platform level, at the facility level, and then you stop, right? So this is a good diagram to show how data-driven model with BHP can reconcile with some of the tests. As you see, this is flat, and then somewhere around this time you see a aquifer influx, and then the water gas ratio increases. And this is a well test that was done with operational accuracy and reliability as told from the field. And we were able to nicely cut through it, which shows that the model was able to measure it. Now, this is just a cartoon diagram, just a representative diagram, but we'll see more pictures as we see the case studies now. So let's also understand how this model is going to work in terms of orchestration. So data ingestion is going to be something simple. You'll require daily production data, wellbore data, PVT, well completions, and your gauge pressure measurement. What you'll do once you ingest the data, you'll do data cleansing, which is your prior data cleaning and pre-processing, where you remove the invalid data, remove the nans, do a downtime filter, apply downtime corrections, remove noisy BHP. You can set certain trends, and you can set you can set certain cutoffs outside which you may call it gauge drift and other kind of things. Also, if there is any gauge drift or gauge malfunction that is reported from the field, you may want to remove that data. Once that is done, you need to do data aggregation, where you need to homogenize data to a consistent frequency, because data could have the times could have big gaps, so you may do some interpolation in between. You may want to do some steady state detection to remove the periods where you see transients in the wellbore due to liquid loading and other reasons. Once you've gotten this nice steady state detection, then you calculate your BHP using the data-driven model in multiple iteration as shown in the workflow before. Once that is done, you calculate your BHP accuracy and your errors, and you report your water gas ratios. The whole optimization and exploratory analysis is then followed by validation and testing, where you measure your residuals in terms of pressure and water gas ratios. You reconcile with the tracer measurement. After you've done the whole optimization, you can reconcile with your field level measurements. And then you also try to find that if you see certain jumps or fall in the water gas rates, you can go at platform level and at well level and try to understand what must have happened there. So you can reconcile it also with the well shut-ins and workover events, which we'll also see in some of the case studies. So this is the first case study, the simplest. we are producing from a well which hasn't seen any sort of aquifer support. It is producing from the normal cornet water saturations. And therefore, if you see, the water gas ratio is flat in the second diagram, if you can see in this picture. This is the gas rate. I mean, there were periods of there were periods where the data was noisy, and you can see that this blue, which represents the calculated BHP after the WGR optimization, the whole workflow, and the black being the gauge measurement. And the measurement are really, I mean, the whole history match is extremely accurate, and that establishes our confidence on the predicted WGR. But we also show the two tracer measurements here and here, and we show that the model's prediction matched reliable with the second tracer measurement, which was in November 2022, while the first measurement was deemed unreliable due to sampling inconsistencies, which was reported from the field and from the test itself. So we are able to strike out the data of tracer, which is not so reliable, which is often the case, as I've explained, because firstly, tracer data is qualitative, model interpretation, and then lastly, sampling inconsistencies and operational failures. So those kind of things have been taken into account. So because it is having in the cost function both BHP match and tracer, so it is always able to eliminate the bad data. Now, what if I have a case where I am producing from cornet water saturation, but in the middle of the production, I open another formation and I start producing commingle. So this is one of those cases, right, where you're producing from multiple zone. You start with zone A, you open another formation, so you now produce from zone A and zone B. So you have two perforations and two formations, basically commingled production. And then after a certain point of time, you close the zone A from which you were producing, because your water gas ratio has gone higher, and you found that zone A had higher water gas ratios. Now you only produce from zone B. What happens here? You need a multi-segmented approach in water gas ratios to be able to solve this problem, because every time you open a new zone, it will come up with its own water gas ratios, right? And that's what we've been able to do here. We've been able to create multi-segmented approach so that every time you open a new formation or close a certain formation, you give yourself a chance to recalibrate or retune your model in segments, and therefore you see there is a change in WGR, which is what you expect by physics as well, as you open another zone, commingle the production, and then you close another zone. And it also shows why it was done, because you had a higher water gas ratios. They opened a zone for a very small time and then they closed that zone, and the new zone produces a lot lesser water. Also, you can see while doing all this, you made sure that your history match of your bottom hole pressures are very reliable and accurate. And at the same time, you were also able to make sure that the only tracer measurement that you've had was in line with the water gas ratios that you actually predicted in this time. Now, understand, these are all very simple cases because there was no underlying water volume, and therefore you were just producing from the cornet initial water saturation. But case can get very complicated when you have an aquifer influx, because then when does the aquifer actually start showing its effect? When it penetrates, these kind of things become very crucial, and we're going to see that in our case study, so don't worry, bear with me. Also, what you would see is that in this case study, there were a lot of shut-ins. Some of them were long. As you can see, there's a nice buildup here, then it's falling down, right? So these shut-ins, and it can also be confirmed from the gas rate. These shut-ins are also a part of your BHP data. So this is attributed to our BHP filtering and our steady state detection, that we were able to eliminate these periods, because no way your multi-phase correlations will work here, right? It is meant for steady state and flowing periods. And we were able to accommodate all that. So this is again attributed to steady state detection and the data pre-processing and cleansing, which we put so much stress on when we were explaining the model. So let's move to another model. This is a model where you have seen aquifer influx late into the well life of the well, and which was also confirmed by the measurements at the platform level. Now, what does the algorithm do here? It shows a flat trend up to here, which is also confirmed by the tracer, and it detects water breakthrough somewhere here in the January of 2021 or a little bit before that, late 2020. And then it shows an increase or a spike in the water gas ratios, and then it again flattens out towards the end of 2023. It aligns well with the tracer trends, matches the tracer water gas ratios, eliminates the water gas ratios that do not make a lot of sense, because your water gas ratios are not going to decline once they spike up because of and also we were told about the sampling and consistencies of these methods. Also, you would see that the BHP history match is so accurate, but then again back to the same point, right? Look at the shut-ins that you've had, long shut-ins, nice buildups throughout the history of the well. So not just that we aligned with the tracer trend, not just that we were able to predict the water breakthrough around the correct time if you look through the picture, but what we also were able to do is we were able to eliminate the shut-in periods and the periods of noisy data. If there were, in this case there were not, but often you will see gauge trips, we can also eliminate those data. So we are cleansing the BHP data, we are fitting a physics-based model, and we are using a data-driven water gas ratio curve to explain the physics of water gas ratio evolution. So a lot of things happening parallelly if you understand the algorithm. Now we look at a case where wells did not have any aquifer support, but they had frequent shut-ins. Now, this is not a new case, by the way, because we've been seeing these cases a lot in the previous cases as well, right? But this is just benchmarking one of those cases where we saw shut-ins continuously from the period of March 2019, March 2019 up to late 2020. And in the middle of all that, we also saw that another zone was opened, and initially we were only producing from the perforations of zone B. Now the production started from zone A and zone B in a commingled sense, and they were not just shut-ins in certain in 2019 and 2020. You also see there were some BHP some gauge failures, and those were also accommodated, because if you see in this region there was a lot of production, but still see pressure spikes and pressure behaving absurdly. The benefit of this method was that it was not just able to eliminate the shut-in pressures, but also these anomalies which do not arise from shut-ins, the pressure peaks and the pressure falls. It was able to eliminate all that, and it was able to basically detect your steady state periods of flow and fit through a water gas ratio curve through this, and it was able to produce you a good history match of your BHP with the gauge measurement. So another benefit of this hybrid virtual metering method, that it's able to do so despite so much noise in the BHP and also the shut-ins and everything. And also, it identified the increase in the water gas ratio due to commingled production and water influx from a new zone. So, I mean, it highlights a lot of features of this model, right? I mean, how it is able to deal with operational challenges, how it is able to adapt from, changes in changes at the formation level when you're producing from one formation versus two formation. And in between all this, it is still able to history match the pressure profile very accurately. Now, this is a case where you had a long shut-in from here all the way to here, from 2019 January all the way to mid to late 2021. And the model, further, that shut-in is all obviously confirmed from your BHP gauge measurements. The model is able to accommodate this shut-in, and because of the physical consistency of the model, which is not just data-driven model, a data-driven form of water gas ratio, which is also not completely data-driven because it's inspired from your Berkeley-Leverett curve. But on top of that, the multi-phase flow equations, because of the kind of equation which is accommodated in WGR, taking into account what the physics of this whole phenomena is, it is able to keep your water gas ratio constant instead of increasing or decreasing it, which can happen in a machine learning model because there's no physics constraint on it, and therefore you can very well have a you can very well continue on the initial trend because there was an aquifer influx. So if you understand a weak aquifer influx, so if you understand the water gas ratio started to increase, inclining, the slope inclining upwards, there was a shut-in, it flattened out, and then it continued from the same value when you again started production. What it shows is a lot of continuity, right? These kind of continuities can only be possible when you have a physics constraint. And therefore, the model effectively handled the well behavior under weak aquifer support, frequent shut-ins, ensuring reliable reservoir monitoring, and it was able to maintain continuity of the model and continue the same sort of increase once the shut-in ended, and kept the WGR constant under shut-in. Again, stressing on the same point that in the steady state detection period, look at the BHP history match. So this well is a bit contrasting to the previous well that I showed here, because initially it did not see any aquifer influx, and aquifer influx was seen somewhere in the middle of the production history. In this well, you feel the aquifer influx from the day one of your production, right? So these kind of detections tell you what is your water breakthrough time and keep you more prepared in terms of planning your well shut-ins and interventions and all kind of things. So we also were able to do a field scale history match with the tuned WGR for all the 40 wells. And this is a diagram showing what we have seen before as well. BHP calculated. BHP base was if you would have taken the constant WGR that you found from your first day tracer measurement, or if you would have updated only after the tracer measurement, that we called it base, basically your tracer profile of your water gas ratios, which essentially means something like this: a flat line from here to here, then a flat line from then a flat line from here to here, and then a flat line from here to here, flat line from here to here. So basically between two consecutive tracer measurement, you take the last one as the constant value. So essentially what you do in back allocation, right? You keep updating after a certain period using your sparse measurement. Based on that, we calculated our BHP base, and based on our real-time water gas ratio prediction, we calculated our BHP calculated, and BHP gauge is what was known from the gauge. If we compare our model and if we look at the results, we have 23.6 psi drift from the gauge pressure measurement in all the 40 wells, which is our P50 error, median error. And the P90 error is also 136 psi. Now, please understand what is the range of pressure we are dealing with here, right? If you look at any of the case studies, we are dealing with pressures as high as 2,000, 1,000, 5,000, 1,500, right? So if someone tells me that in a range of 1,500, 2,000, 3,000, you're off by 136 psi in BHP, which, by the way, even with a gauge, you go with certain sort of calibration errors and whatnot. I would take that. And that is a P90 error, by the way. So the worst case scenario, right? So this history match confirms that our model, because it was using a multiphase flow model, it was able to keep the physics of everything. From the tracer results on a well level, we've shown that it is also able to honor the tracer trends. But what if someone asks me that, okay, tracer tests are not reliable, tracer tests are sporadic, and tracer tests are only available on limited wells? Do you have any sort of method to confirm me that your measured WGR, forget about the BHP history match, right? That could be model tuning or whatever. Does your WGR make sense? Is there any kind of benchmarking or measurement that can add more confidence to the water gas ratios and the water rates that we calculated? My answer would be yes. And that confirmation comes from my field scale water rate match. Now, this is my calculated water gas ratios, calculated water rate, which is shown in the black. The orange is the water rates that are measured at the platform level. So basically, it's a plot between water rates measured at the platform level, at the facility level, and black one is the what you calculate from our real-time method. Now, there's also a blue point which is indicating the calculated water rates with certain wells which were missing gauges. So we added some sort of delta buffer for that. But as you can see, they're not far from each other. So, I mean, that buffer is just to accommodate a couple of wells which were not producing a lot of water and which were missing gauges. But what we see from this is the platform level match and the actual match are very accurate, right, in terms of water rates. But we don't stop there. We also do something else. What we do is we go on some well level major events that happen in after 2021 until mid 2023 in the well history, and we compare our results from the platform level results and try to reconcile what must have happened. Like, for example, we see a 25 STB per day fall on a median basis in the rates based on our water gas ratios in late 2021, early 2022 in the well A because of shut-ins. And that fall is shown clearly by the uh, change by the curve of the platform level if you zoom into this curve. What we also see that well B, which was producing commingle from multiple formations, one of its formation which seemed watered out and high water gas ratios was shut in, right? That led to, as per our water gas ratio, that led to a 600 STB per day fall, and that is again confirmed from the platform level measurement. So we were able to confirm two events until now. Well A was shut in, and because of well A shut in, you suffered a 25 STB per day fall in the platform level measurement. Further down, in early 2023, you saw that well B, one of the formations which was producing a lot of water, was shut off. Because of that, you found 600 STB per day reduction in the water rates in the platform level. That was again confirmed, and our predicted and actual matches very well, which you can see here as well. These are the predicted at well level, these are at platform. Further, well C was shut in later in late 2023, which led to another 450 STB per day reduction. That was again confirmed with the match of our platform level results with the actual results. So whenever we saw these big falls in the, I mean, what are we essentially trying to do? If you understand this diagram, I know it could be complicated sometimes. We are trying to find all the major reduction in the water rates and trying to go back into why this reduction must have happened, the root cause, right? Like, for example, the first reduction in this late 2022 is because of Valley shut-in. The early 2023, the one shown in blue, is because of well B water zone shut off. And the mid 2023, which is well C shut-in shown in black, 450 STB per day. These are major events that we can actually go and check from the operational field level history. And that confirms that this method could be trusted just with the fact that the trends are making sense with what we observe operationally, and the trends are also making sense with what we see at the platform level, right? So these are further reconciliations of the measure of the numbers that we produce, because numbers can be totally model based, tuning based, and cannot make sense. But because of so much physics, because of so much of investigation further from the results, we were able to show a lot of confidence on these results. So what did we learn from this whole hybrid virtual metering method that we developed? I mean, we were able to accurately estimate our rate. The model estimates the rate accurately. The model manages the multiple zones and commingling and the shifting of zones through multi-segmented approach. It was also able to address data quality in terms of the gauge drifts, the gauge malfunctioning, operational disturbances, and frequent shut-ins and whatnot. The BHP history matching, even in the scenarios that involved aquifer support, multi-zone production, frequent shut-ins, gauge drift, was the key. The detection of the steady state and the history match in that steady state. And the anomaly detection, which we showed and confirm, which was shown and confirmed from the field level measurement, was able to prove further that you can actually you can actually reconcile at any stage whether your model is in line with your platform level measurement, and also the detection of water breakthrough, which we've shown in one of the wells, that could be detected. And because of that timing of detection, you can manage your well intervention and shut-ins and everything else ahead of time. So this is my presentation. I hope I didn't go too fast. If you want any further explanation, feel free to ask questions.
Thank you, Utkarsh, for such an informative presentation. We do have a few questions in the chat, so I'll go as they came. So one of the question from Keys is water gas ratio associated with condensate water should increase threefold as reservoir pressure decreases threefold. I think it's pertaining to some of the graphs you were showing in the case studies.
The water gas ratio should increase. I'm not sure if I've gotten the full question, but I will go back to the plot again. So water gas ratio, if you have cornet water saturation, will not be affected much, because you're essentially producing, I mean, if you go by the material balance laws or anything else, you're essentially producing from the same saturation essentially, right? If you go by Berkeley-Leverett two-phase displacement laws. Yeah, your water gas rates can change a lot because your gas rates are varying, but your water gas ratios, if there's no aquifer present, if you're producing from your cornet water saturation, should not vary much, and it should rather be flat.
Okay. I have a few questions I wanted to ask, and I also request the audience to put their questions in the chat. I see another question. Can you please say a little bit more about the steady state detection? Do you use derivative as a criteria, for example?
So steady state detection period is not essentially done on derivatives, but it is done more on basic rate steady state detection. So you take windows of rates and you see that the rates which fall within 75 percentile of that particular window, you can take a weekly window, you can eliminate some of those, plus all the rates which are all the pressures which are pertaining to a very small rate. Let's say, for example, you set a cutoff of 100 MSCF per day. It's a low rate, right? For a field, offshore field, it's a low rate. So all the pressures that pertain to such a low rate, you eliminate them from the history matching function. So, and then if you have shut-ins, remove all the pressures of the shut-ins and you only keep the flowing periods. So yeah, it's a data-driven approach where you basically eliminate the anomalies. You can use a median filter, you can use some other filter, signal processing techniques. On top of that, you also eliminate unphysical pressures if they exceed a certain values, which you don't expect them to. And also remove rates which are too low, because on those rates, your flowing multiphase correlation may not be so applicable. And if you have certain periods where you observed, from the field, you've got an operational information that you observe liquid loading or something which is, sort of transient and causing a transient phenomena in the wellbore, it's good to remove that, because we are using steady state multi-phase models, and therefore they will not be applicable in the cases where you have liquid loading or liquid fallback. So.
Yeah, thank you, Utkarsh. I think there are some more comments from Keys, but I think I'll repeat one more time, but I think maybe Keys, you can take it offline and reach out to Utkarsh to get more clarity. It's another question is, my question is on the minimum variation of water gas ratio that can be detected based on BHP match. I would assume there is a lower limit, one barrel per MMSCF, or what's the minimum variation of water gas ratio that you can detect?
So this is the thing, right? Yes, you can set a minimum limit. We have done that too, but there is no universal lower limits to this, right? I mean, that is depending on what asset you're working on, what has been historically seen. I mean, for in certain offshore, you can set it as low as 0.5 STB per MMSCF, which is essentially meaning that those wells are dried out mostly, right? You can go even lower than that. But that really depends on the asset, right? It's an asset-based number. You can set your limits in the optimization, but those limits are never going to be universal. If you do so, I mean, what is the loss? If I set the limit from 0 to, let's say, 10,000, what is the loss? The loss is you open up your model to a large degree of freedom, right? You waste a lot of time computationally. But yeah, you can see fields where it can go as low as 0.001 STB per million cubic feet, for the simple reason that those wells are dry wells. But are you interested to measure water breakthrough in a well which is essentially dry and you're not producing any water? I mean, the whole purpose of measuring water gas ratio is to understand that there is a flux of water that is coming and you should have preparedness to handle that, right? But if you have 5 barrels, 10 barrels of water, nobody is necessarily interested to have too much time in, investment or too much planning in handling that. So I hope that explains the question. But yeah, the specific answer to your question is there is no universal lower limits to it. You can set lower limits of with using a buffer of what you've seen on the fields or what's historically been seen. So
Yeah, thank you, Utkarsh. Another question, do you think this method will work only on surface measurement if you don't have any downhole gauges? Is there a way to adapt it?
yeah, that's a good question. So what is the physics of this model, right? Multi-phase pipe flow model. If you want to use this method on the surface, what do you essentially need? A choke model, probably, right? You can use a choke model. In fact, what you can also do is you can do both wellbore and choke model and do a nodal analysis at surface. And by the way, these things are not new. People have tried these kinds of methods. But the main thing is you need to understand that the behavior of wellbore, if I do a nodal analysis at a surface level, and let's say I use a choke model as my multi-phase model, will the displacement of water and gas within the wellbore be identical to how it is in porous media? Perhaps not, right? So this whole theory of using Berkeley-Leverett in the formation is a well-known immiscible to fluid displacement, right? It's coming from a benchmark method. The displacement may not be the same. So we may have to come up with an equation that aligns better with a pipe based two-phase flow, sort of physics. Berkeley-Leverett we are using because here, if you look at water-gas ratio when it enters, essentially what are we doing in this method? We are doing a nodal analysis at bottom hole. What is the inflow source? The inflow source is water-gas ratios that come from a data-driven method. What is that data-driven method shape inspired from? Berkeley-Leverett, right? So yes, long story short is it may not be used as it is for surface level models, but the theory can be translated to surface flow models, the essence or the principles, if that makes sense.
But the accuracy is better if you have downhole
Yeah,
engineering.
because the physics has been taken keeping downhole gauge measurements into picture. Yeah.
Yeah. Okay. Utkarsh, another question from my side is you talked about this hybrid virtual model. What's happening behind the scenes? Can you talk about like what algorithms you're using?
Yeah. No, actually, I'll go back to the same thing. So it's a very simple algorithm that you have you observed from Berkeley-Leverett that your fractional water flow and water saturation have a sigmoid similar to a sigmoid shape, right? Because of that, we were inspired to take that your water gas ratio and your GP, which is your produced gas rate, the cumulative produced gas volume, essentially. That will also perhaps follow similar shape because they are related to each other, indirect proxies of each other. And because it follows that shape, we can model that shape using a 4-parameter or 5-parameter logistic regression. Now, what is that logistic regression going to optimize as a cost? Essentially, it should have been water gas ratios if you had MPFMs, but we don't have MPFMs, right? We have just sporadic 1-2 water gas ratios. So what you can do though is you have gauge measurement. You take that WGR, you take your wellhead, your wellbore geometry, you take your deviation survey, you take your gauge pressure measurement, you take your PVT, you take your wellhead pressures. You have everything now, including the predicted WGR to predict your bottom hole pressures, right? Now you have a cost function. Your bottom hole pressure predicted minus the bottom hole pressure that you get from your gauge measurement. If you are able to optimize that by optimizing these 4 coefficients, you can get these coefficients. But there is a catch. We also have a penalty function, if you remember. If I were to repeat my
Yeah.
slides, I don't mind. That also makes sure that while you're doing this, you also don't diverge too much from your tracer measurement, which makes sure that your tracer measurements are honored as much as you can, right? This function, the penalty function, is predicted water gas ratios on the days of tracer measurement minus the tracer measurement. So even though you're doing a BHP history match, you make sure that you honor your tracer measurement, or not just tracer, but any kind of measurement that you have. You can have MPFM measurement. We showed well test measurement also in this case, right? But this is a penalty function that optimizes your coefficient under BHP history matching, keeping this constraint true.
Yeah.
Does that explain? And this is the 4-parameter curve of water gas
Logistic.
ratios versus GP that we used, with these being the main coefficients.
And I think the natural question that comes after that is that you mentioned you use logistic regression, but can you use more sophisticated machine learning models?
Absolutely, absolutely. We can use anything, including all the fancy deep learning models, right? But one of the reasons we used logistic regression was because it's simpler to handle. You have only 5 coefficients as compared to a machine learning model, deep learning model, where you may have 50, 100. And secondly, logistic regression, our main motivation was that its shape is very similar to what is your Berkeley leverage shape. And therefore, it is easy to handle something. For example, your lower asymptote, your upper asymptote, your point of symmetry, your slope of the whole curve. But being said that, right, let's say for a moment we want to give this method more freedom and we want to forget Berkeley Leverett for a moment. We can use a deep learning method. We can use a RNN or anything else. The whole logic is going to be from here, where you detect your WGR and write up physics-informed neural network method that calculate BHP on top of that WGR, and optimizes the coefficient of that deep learning method. It's totally possible, but you need to keep some sort of constraints on your deep learning model to make sure that you don't create a shape of WGR that may not physically make sense. Although you will still have this BHP constraint, so I believe it will not do bad. But yeah, I mean, this is the thing, right? When you approach a problem from industrial point of view, given the adaptability and computational speed, you always go bottom-up approach instead of top-down, right? You take the simplest and see what are the issues there, and then you take the next complicated step. And thankfully, logistic regression is a good enough approach for the kind of problem we've seen.
Do you think the availability of data is also kind of a challenge to apply machine learning?
Yes and no, right? I mean, depends on the history of wells, because it's a gauge measurement. If you have a high frequency gauge measurement pressure available and it has, after data cleansing, you have a good enough size, then I think the availability of data will not be a constraint, right?
Okay.
So thankfully, we are measuring gauge pressure here. So say if you have 10 years of history of production, which is very normal in offshore wells, right? You will have 3,600 days essentially of rates. Even if you eliminate all the bad data, I'm sure you'll be left with at least 2,000 to 2,500 days, right? I don't think it's too bad to use a simplistic machine learning method. Yeah, you can't go too complicated because you'll not have millions of data here. We will never have that in oil and gas, right? But also understand that sometimes you can have high frequency measurements of of the gas rates and the pressures, right? In that case, you can have 100,000s of data as well if you have hourly measurements of gauge pressures and gauge rates, and venturimeter rates. So I wouldn't say data is the main constraint. The main constraint is how you are able to control the shape. And if you're able to do so using a deep learning method, you might as well do that.
Okay. So Utkarsh, we are almost at the end of the time. Anything you want to say in conclusion? Any next steps or any new work that you're looking for?
I think this is itself a new step that you mentioned, that probably we might want to bring some level up model, data driven, maybe something like a simple support vector machine, or something which can also be deterministically controlled, or maybe a decision tree, but we need to have some sort of constraint. So we may want to think that the next step would be to bring some function which can offer more non-linearity, but we can have control on the shapes and have a more refined machine learning algorithm. That is one of the things. And second thing is we want to see how we can do if we do not have a prior information of condensate gas ratios, and we can bring in some PVT model to accommodate for that, how the model performs in that scenario. If we are able to do that, then I think we can refine it even further.
Thank you, Utkarsh. One more question came in very quickly, if you can answer in a minute.
Mhm.
How do you handle multi-zone completions with different water breakthrough behaviors?
Yeah, so this is the case I think he's talking about, and I'll take the water breakthrough case itself. This one, uh,
Mhm.
this one, right? Although it doesn't have a water breakthrough, but it can handle water breakthrough from the same logic. What we do is every time we have a operational information that there is multi-zonal. I mean, that information has to be provided at an operational level. Obviously, that you had a change at formation level. Now that change could be because you opened a new formation and produced commingled, or you shut off one formation and produce from another, vice versa. Uh, You need to update the new PVT based on the new formation that you open. And what the model does is it stops right there where you made your formation level change, which I can show in this diagram nicely. It stops right there, and it restarts the whole model from the new segmentation, which is essentially that date where you made that zone level changes. Then it stops again there where you made another change and restarts the whole model from there. So basically, how you do a segment level fitting, right? You do it in multiple iteration. You fit something through a first segment, and then you stop, then you reset it to 0, and then you start producing from here. If I were to explain from this picture, this is or let's see which is the best WGR picture to explain. I think this is a good one. So here you have water gas ratio, and here you will have date or your cumulative gas volume. You're producing this curve. Let's say on this date, you have a formation level change. Now you will reset your GP to 0 here, although your GP is not 0, but you reset it to 0, which is difference GP, and you restart the curve from there. Does that explain the question?
Yeah, I think so. Um, I think we are almost at the end of time, so we're not going to take any more questions. But thank you so much, Utkarsh, for your insightful discussion, sharing your insight here. And I would encourage the audience, if you have any more questions, you can always find Utkarsh and bother him on LinkedIn. I'm pretty sure he'll answer all the questions. But one before we go, once again, thank you, Utkarsh, and
Thank
I'm
you.
gonna
Thank you for
post the
having
links
me.
again for the SPDACATS one-day event that we are hosting in the end of September. Please check it out and join if you're interested. I think it'll be very interesting. So, okay, with this.